emotions.
It's epic! Hey, kids. My name is Dr. Krypton. And I'm Dr. Xenon! Woo! And I'm Dr. Neon! Sisters, unite! Oh! Okay, never mind. Anyway. So, kids, today we're learning about chapters 5 and 6.
And those chapters are about electrons,
Periodic table. And atoms.
Yay! Now we're going back in time to meet Mendeleev, and he's the guy who created the periodic table.
Let's go! Woo! Today.
I'm doing fabulous because I just laid out the whole periodic table.
Really?
Wow. Yeah.
Exciting.
Well, you see, the way I set it up, there are 3 different periodic trends. First, there's atomic radius, and it increases from right to left, and then from top to bottom. And then, the second one is ionization energy, along with electronegativity, which is the third. And both of them increase from left to right and from bottom to top.
Exciting. Did you hear that, kids?
Yeah! You have a great group of students.
Thanks, I know.
Is that all you needed to know today?
That's all we need. Thanks, Mendeleev.
You are so welcome.
Have a great day.
Thank you. You too.
Bye.
The metals, which are right here, they are good conductors of heat and electricity. They have a high luster. They are solid at room temperature, and they are ductile and malleable.
These elements over here are nonmetals, which are poor conductors of heat and electricity. They are gas at room temperature and are the opposite properties of the metals. These are the metalloids. They have properties of both metals and nonmetals and are semiconductors.
Group 1, right here, is called the alkali metals. Group 2, right here, are called the alkali earth metals. Right here are the transition metals, group 3 through 12.
And group 17 is the halogens, along with group 18, which are the noble gases.
There are the diatomic 7, which means that hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are in this group.
Next, we're going to go see Erwin Schrödinger.
Hey, Erwin! Hi!
What are we learning today?
Well, today I'm going to teach you about the different electron models. Oh yeah, here we go!
Ooh, look at these pretty pictures.
Well, the first model is the Dalton model, and it was created in 1803 by John Dalton, and it pictures atoms as tiny indestructible particles that don't have an internal structure. The next model was discovered in 1897, and this is the Thomson model. J.J. Thomson discovered the electron also. This discovery led to his plum pudding model, and this pictures electrons embedded in a sphere of positive electrical charge. The next model is the Rutherford model, and it was discovered in 1911 by Ernest Rutherford, and he found that an atom has a small, dense, positively charged nucleus, and electrons move around the nucleus. In 1913, Niels Bohr created this model, where the electron moves in a circular orbit at fixed distances from the nucleus. The next one, which I developed, I used mathematical equations to describe the motion of electrons in atoms, and my work will lead to the electron cloud model. Let's go! I love chemistry!
our blast to the past?
Oh yeah!
Awesome! Now we're going to learn about electron configurations. Kinsey, can you tell us the electron configuration of iron?
I can definitely do so.
That is
Great!
awesome.
So, as you can see on this periodic table right here, iron is right here. It is Fe. The S block is groups 1 and 2. The P block is groups 13 through 18. And the D block is groups 3 through 12, all right here. Also, the F block is down here. So, iron would be 1s2, 2s2, 2p6, 3s2, 3s2, 3p6, 4s2, and 3d6. Once you go to the D block, you have to subtract 1 from the number of the periodic number.
Do you kids have any questions?
Ooh.
What about you?
What is orbital diagram?
Well, we drew it out. Let's go take a look.
Come on, guys, let's go look.
I have an H-wire.
This is the orbital diagram, and everything that we just said is drawn out.
Wow. That is so cool.
So this is a light wave.
And these are the different parts of a light wave.
The amplitude is the distance from 0, which is straight across the middle of this light wave, to the crest. And the crest is right here.
Wavelength is the distance between the two crests. So from this point to this point.
And the frequency is the amount of waves that go past from a certain position in a certain amount of time.
Let's do a word problem, shall we?
Okay, so if a fluorescent light has a frequency of 3.02 times 10 to the negative 7 hertz, what is the wavelength?
That's a good question.
Let's find out.
Sounds good.
Well, the equation C equals wavelength times frequency. C is your constant of your speed of light, which is 2.998 times 10 to the 8th. So you place it in your equation, and you plug in your frequency, divide by your frequency on both sides to get your wavelength of 9.93 times 10 to the negative 14th meters.
Man, do I love chemistry. I'm so pumped. Let's do another one. Woo! Okay, here we go. How much energy is given off from an infrared ray with a wavelength of 7.13 times 10 to the negative 18th meters?
That's an awesome question.
Thank you.
Okay, so we would have to start out with our equation, and C is the speed of light. So we are trying to find the frequency to put into our energy equation. So C equals wavelength times frequency. 2.998 times 10 to the 8th is our C constant, and that equals 7.13 times 10 to the negative 18th, which is the wavelength times the frequency. So you have to divide by 7.13 times 10 to the negative 18th on both sides. This gives you an answer of your frequency being 4.20 times 10 to the 25th hertz. Now we have to put our frequency into our energy equation. Our energy equation is energy equals our Planck's constant, which is 6.626 times 10 to the negative 34 times our frequency, which we got from the previous equation. So to find our energy, we would do 6.626 times 10 to the negative 34 times 4.20 times 10 to the 25th. And this gives us our energy answer of 2.78 times 10 to the negative 8 joules.
Yay!
Good job!
Now that you've so wonderfully mastered chapters 5 and 6,
Let's have pie. Woo!